It's a great pleasure to have Debajyoti Sarkar here from IIT Indore to tell us about some recent progress on excited state economy.
Yeah, thanks a lot, and thanks for having me here. So I'm going to talk about this work. The most part of this work that I'm going to talk about appears in this paper, came out last month. But I will also briefly discuss some of our past works, although maybe some of you have heard me talk about those things. So, so my outline of the talk will be, introduce some basics, discuss the setup, and as the title suggests, I'll be talking about modular Hamiltonians in excited states, and the types of excitations we'll have in mind is, excitations of where you have some perturbing operators along some spacelike or null slices, sometimes in the past and future wedges. I'll discuss both of these things. And finally, I'll discuss KMS conditions before wrapping it up. So, so as I said, we'll deal with basic aspects of density matrices and subregion and extended modular Hamiltonians. And motivation-wise, at the very least, you can think of it as, extending the pool of examples where the modular Hamiltonian is known. It's only known in a handful of examples. And historically, I got interested in this problem from applications in ADS CFT, such as, for example, in bulk reconstruction problem or understanding emergence of space-time. There also modular Hamiltonian plays a role. So some introductory comments. So if you have, let's say, some factorizable Hilbert spaces, defined on some slice with consists of two subregions A and A bar, then you can define subregion density matrices like this, and the corresponding modular Hamiltonians HA and HA bar will be these. But of course, in quantum field theory, a better defined quantity is this modular operator and this extended modular Hamiltonian. And only when you have a factorizable Hilbert space like this, you can also define the subregion quantities, rho and H's.
Well, why does this avoid this UV divergence issue?
Yeah.
Can you give some equation as to why? Is it obvious or?
Yeah, so apparently these H's are, they give states of divergent norms. And these H's, sorry?
And the divergence cancels?
Yeah, here they cancel out. Exactly.
Geometrically, it's like a solution which doesn't introduce any singularity.
Right. Yeah. Right.
If you do a modular boost at wedge, then you boost only this side, not this side. But when you do that operation, which is the operation with respect to that charge, HN minus HN bar, you do this. So it's smooth at this point.
I would think you're doing this.
No, it's a boost.
It's like the bifurcation point in the other side. Some side is black, right? Nice. So this is H minus H, killing vector. Yeah. Okay, thank you.
So we'll be interested in the actually the modular Hamiltonian HA or this extended counterpart H for excited states obtained by perturbing vacuum state by unitary operator U. And we'll see that the non-factorizability of Hilbert space in QFT, which is generically that is true, shows up in an interesting way in these quantities.
Sorry, and again, that HA minus HA bar in Rindler space is just the Killing flow, whereas just HA would be in one wedge.
Yeah. All right, so this will be the setup. So for most part, we'll be talking about Ringler half space to be the A. So it's a semi-infinite space. In this case, it's indeed boost that we talked about. And we'll have these two types of perturbations that I mentioned. One is where I have some Hermitian operator On of modular weight n. I'll come to the definition of modular weight in a moment. Integrated with some support function f over some spacelike or null slice sigma. And this quantity inside the integration I'll call G. So the unitary operator is e to the minus I epsilon G, and that's acting on the vacuum state. And you can study this change of states as order by ordering perturbation inlet. And what is this modular weight? It's essentially how it, for the Ringler subregion that you have in mind, it's essentially how it changes under the modular flow. My definition of modular flow will be this. You take an operator On and you evolve it with some modular time s by the vacuum modular Hamiltonian. It's a vacuum modular flow. It's defined like this, and if it has modular weight n, then it essentially goes to this quantity. So it picks up a factor e to the ns. So for it,
that flow both sided or one side?
this is for both sides.
Both sides. Huh?
Yeah, so I'll denote them by this left right.
Basically rotational charge, right?
Right,
Just the spin.
exactly. Exactly. In this case, it will just be. So, for example, for P++ stress tensor perturbation, which I'll discuss briefly, it will be to the 2s. But I actually won't be talking about this part too much, and I'll mostly, this is some old work, I'll mention the results, but I have some backup slides on this.
And that state was made in Euclidean space?
Uh,
That perturbation was in Euclidean?
well, you can,
Valencian?
but it's for now everything is Lorentz. Everything is Lorentz.
Because the operator is integrated on the Cauchy slice.
Yeah.
I see. I see. I see.
So there's some unitary acting on this.
I see.
It almost looks like a factorized unitary, but I guess it's not because you can have.
Yeah, that will be determined by how G. We'll discuss that.
But why does it look like factorized? The sigma is supported everywhere, right?
Yeah, but it's the integral of the local operator. So you might be tempted to.
We'll
I
spend
see.
some time on this.
It's like
Yeah.
factorized. It's
Yes,
like
but
when I
it's
say,
not.
But it's not.
O can be.
O can be.
O can have like derivatives and x and stuff. If it's very, the non-factorized thing is very close to x.
Right. And that's, if it is factorized, then the relations will be very simple between the excited state modular Hamiltonian and the vacuum modular Hamiltonian, but otherwise it will be pick up some extra contributions.
Right. Yeah, it will be the same, right? In fact, it is factorized because it's local unitary.
It will be a commutator, for example, first.
Yeah.
We'll see.
Right.
So the setup is what this O has support on one side.
You know, the O has, so this, so your subregions are A and A bar.
Correct.
But there is a, let's say, so for the first example, which I won't be discussing too much, there is, let's say, a slice, which could be either spacelike or fixed time slice or null slice, but passing through the endpoints, meaning the point where A and A bar touches that surface. Yeah, the function could be, this operator could be supported all over that surface.
So spacelike, I kind of understand what, you know, after the action, the question still continues to hold. But how do you understand that if that sigma was null? If you can draw the diagram?
So basically, for example, what I have in mind is, let's say you have stress tensor perturbation. So then, you know, for holomorphic factorization, you have, let's say you take a T++ perturbation. So it's T++ is just supported over C. That's what I mean. The black points.
No, I understand, but how do I make sense of so just to understand the state, I would like to have a spacelike surface on which this space is defined. The state is defined, right? So if that state involves an operation by a null operator, how should I slice the space along space-like slice so that now I have a state, now I can now ask my questions. Because the null slice will continue to intersect that any space-like surface, right? If you can draw the Penrose diagram, you will see.
Yeah.
But if it is space-like, then of course you just go a little bit above that, and then you can have a space-like slice. That sigma is not intersecting.
Very nice. The slice is large and we rewrite everything in terms of
So in some sense, kind of limit of null. But
yeah, like
you
imagine
the
space
start with the space-like and then slowly take that limit. That approaches null.
It is that some limiting sense.
No, but in the limiting sense, you will also get the backward going part of that also, right? Because if it is space-like, the Penrose diagram will look like that.
Yeah.
Right? You have to come back to I naught or whatever it's called, right? That's space-like.
But your f of x in yours. Okay, maybe I don't know. Let's see. Right, zero rapidly.
Maybe, yeah.
Yeah, so actually, in this part, what you can do is you take some space-like slice, which let's say with some tilt parameter, tilted from the null line, and you can study this null limit as this theta goes to 0. Yeah. And then you can also have some operator insertions in. So when you have the Rindler half space, then you have these 4 wedges, left, right, future, and past. So you can also have some operator insertions in the future and past wedges. And for that part, we will, to kind of set the stage, we'll consider some local operator insertion to begin with, and we'll see what results we get. All right, so we'll work mostly in CFT2. We'll have some generalization, especially for the stress tensor perturbations and for other perturbations also, but mostly for the first case for arbitrary dimensions. And we'll only consider first order, although for stress tensor perturbation, you can also very simply discuss higher quantities in lambda, meaning higher order changes delta 2HA, delta 3HA, and so on, for arbitrary orders.
Did you say what the motivation for taking this type of states is? Why are we interested in the case with the acceleration as it is not? I presume that you want to eventually find modular Hamiltonians for the states like this.
Yeah.
Yeah. But what is the
Right, so we wanted to consider a situation where the perturbation not just acts on A or A bar region,
right,
but also have some support, over either the endpoint or that the perturbation does not factorize.
correct, but did I miss the point where this becoming null was somehow interesting for you?
So the null case is, as I said, can be understood as a limit of this some tilt parameter, or it's otherwise, it just not it will make some simplifications in
Also, some operators are nice, right? Which are supported on null.
Like if I have massless,
Integral of t plus plus along the
Base t plus plus, that is it.
That's
Actually, t plus plus perturbation will be the simplest case because you can study the excited state modular Hamiltonian by some conformal transformation as we will see. And you will see that, the generic result that you have for this perturbation is essentially very quickly, simply captured by this. Yeah. So a good amount of literature actually exists on, relating change in density matrix with change in the modular Hamiltonian. Most of the papers that appear, they give some formal expressions between, changing this modular Hamiltonian and changing the density matrix. Onkar also worked on shape deformations under that, how modular Hamiltonian transforms. But our goal will be to do more with those formal expressions, investigate them really closely because it involves some subtleties which I missed. And especially in this CFT context. Okay, so so if you really had factorizable Hilbert spaces and let's say your perturbation factors then like this, GA plus GA bar, then the way G is defined, you remember U was minus I epsilon G. So the unitary operator actually factorizes between UA tensor to UA bar. And as a result, everything, just gets its own unitary uplift. And the first order change will simply be this commutator. So whenever I say delta H commutator for the rest of the talk, I will mean this sort of quantity. But what about, something like GA tensor GA bar? And not GA plus GA bar. Then actually these simple expectations will not hold. And then we'll see what we get.
Sorry, H0 is vacuum?
Yeah, so H0 is a vacuum modular Hamiltonian, which will be, going to H by UH with that. Yeah. So yeah, we'll always have that in mind. So we know H naught, we know rho naught. We will perturb the vacuum. We'll know delta rho naught, and in terms of that, what is delta H? So what we'll see for these space-like perturbations is that there is an explicit endpoint piece that adds to the delta H commutator term. And in particular, and I'm just stating the results here, I'm not going to the details. For perturbations via, let's say, this ON, this modular weight N operator, this delta H becomes a sum of lightray moments and their descendants over the X plus horizon. So the form looks like this. This theta, this theta is the tilt parameter that I was talking about. So you can see that you have these various operators, moments, with X plus to the K plus L, their descendants, and you have a sum over them. So for example, the simplest case will be stress tensor perturbation where N is 2 for T plus plus, and then this endpoint contribution will simply be this NA proportional to this NA complex. So indeed, because this will be the result when G is GA tensor GA bar of this form, or rather when this perturbation is over some space-like slice, which also goes through the endpoint, straddles the endpoint.
So why is the index N?
Yeah, this index N was this modular weight, which was defined like this. So it's basically, how it transforms under boosts. So for T plus plus, it will be like, it will go like e to the 2s. And as Abhijit said, it's like spin for boosts.
Is H0 a local operator in general?
Yeah, it's we say that it has a local structure, it's an integral over stress tensor.
Then where's the boost?
Generates the boost, yeah.
So endpoint means origin of space. Right?
Yes, in this case, the origin. But if you, I will have that example. If you have some arbitrary U to V region, you can study exactly the stress tensor perturbation, and there will be two endpoint contribution coming from both U and V.
So it's clear that n equals 0 should not give you any endpoint. There it's what? I was thinking that n equals 0, the operator actually looks like it's a factorized operator. But n equals 1, I'm not able to understand.
Yeah, it's a bit difficult.
Understand why n equals 1 also doesn't give.
So one, I guess, thing that you can check is that if you put up, let's say, a probe operator at the origin, and then you study, let's say, the OPE with some ON, then in this OPE, it only translates, I mean, there is a term like del plus O, only for n greater than equal to 2. Yeah, actually in equal time commutator, that's sorry. So maybe.
So what's the intuition that n equals 0?
Yeah, so the intuition, you can go back to that formula you had for Geo.
This one.
Maybe once there. This one. So if you look at that expression, the exponential of minus I lambda integrals in, at least very roughly speaking, that's a factorized unity. Because it's the sum of something on this side. And I was thinking that the reason it's not factorized is because O can have derivatives in the
So I would say that's the that's what you get by studying these OPs.
Right.
Yeah.
Exactly.
But is there some reason that n equals 0 vanishes, makes it vanish at the origin?
Not vanished, but it's not
Doesn't.
state, right? So it has no size. If you think of some species very nothing, it doesn't entangle things.
And why is the light direction important?
Well, this direction is important.
Right, so that
Yeah.
space like that.
Yeah.
Right? So is n equals 0 saying that there's nothing changing?
Something
like
like
this?
exactly. That was the equation.
But that is also true for plus minus 1.
I was actually trying to do the same thing in my head. I was getting the opposite conclusion.
Okay.
Maybe my n's are minus units. I was thinking that angular momentum n moments decay at the origin like r to the power. Okay. So I from that point of view, I was thinking large n decays faster at the origin.
Oh.
And so it's more. But maybe your n is minus my n.
Yeah, there was an issue with so the indices that comes with let's say x upper subscript plus, that will have n equal to plus, but the superscript will have minus.
Yeah, if you
So
continue this to the Euclidean space, how do, and I've got a wave function with this, I'm not even sure if my questions make sense, but if I had a wave function with this n, would it grow like r to the power n or r to the power minus n? I would expect it to grow like one or the other because, angular momentum won't grow like that.
And I think that higher angular momentum are more supported here.
Yeah, but it could be that this analytic continuing because he's really interested in the lens space. Yeah. Could be that it's continuing to what from the Euclidean point of view would be the wrong side, right? So after the n is the thing you're saying. That's what we normally impose in direction. Okay?
Yeah.
But it could be that for this physical purpose you're imposing r to the power minus n, which would then explain, right? That itself. I don't have the point. It's probably stupid, so please go on.
Yeah, I mean, I have, I think, one equation at one of the backup slides. Maybe we can go back to that later, which discusses this OP, and maybe that can be related also to this decay of angular.
So also, what if this O is a composite operator, which is like a product of derivatives, product of spinning operators? Then this is more complicated, right?
Then this intuition breaks
Then
down.
intuition breaks down. Only in some free field theory where you have a basic operator.
No, but I think this result is more.
Just depends on representation.
My intuition probably.
And this anic result, the
Mhm.
fact that delta H, the additional piece is anic,
Mhm.
that is for what perturbations?
For the stress tensor perturbation.
Stress tensor
T
integrated
plus plus integrated. So it's just, dz t plus plus.
integrated along null.
Yeah. Where was it? Here.
But let me just say one more time for physics. If something has high angular momentum, we expect it to be excited far from the origin. Right? Because things moving far from the origin carry large angular. From that point of view, it seems surprising that high angular momentum no. Anyway, I just
Yeah. But okay, but I mean, what is wrong with this? Like, if the operator that you're explicitly added, the unitary, will have many derivatives in the transverse direction. But you would expect that it's creating more entanglement between the sets. That was what I was saying.
yeah. So maybe I'm confusing orbital angular momentum. Your thing is more like speed.
Or yes, yeah, in the boost space.
But I mean a spin like in the sense that you're putting derivatives.
Yeah, exactly.
Whereas I was thinking more like orbital angular.
Yeah.
Maybe that's it.
Spin.
Yeah. Okay. Yeah, maybe that's it. Okay.
Spin of the operator supported at.
Yeah. Okay, maybe that's what it is.
Right. So this is first order in lambda.
Yeah.
So isn't it true that in entanglement entropy, when one deforms the shape of the entangling surface, the first order variation vanishes, the second order gives you contribution. I think
Yeah, no, but you should say that first order or modular Hamiltonian change.
Yeah.
so and one can show that the entanglement vanishes by taking the explanation.
So just one to follow. So your operator then is just localized at your perturbation is localized at the origin, but has derivative.
Yeah.
But couldn't you have an operator that was localized somewhere else and also carries?
But those would be kind of factored in. Right?
But I was wondering why don't those operators carry large?
Right.
Because Taylor expand your error. That sends it far away.
So you are saying away from the origin.
Yeah.
But then okay.
See, because did you sorry, maybe I missed the context, but did you were just putting a general deformation, right, on the slice and labeling it just by the angular moment. So I was thinking things that were far away would carry large. And those then look very very safe. Why isn't that showing up in this algebra?
Well, it is showing up if you take your support function only to be supported very far away, right?
But didn't his result, sorry, is that support function showing up somewhere in the.
Yeah, that is.
Yeah, this.
Yeah, fine. Yeah. So that's from here. Yeah. So f at 0 is.
Yeah.
Some f0.
Yeah.
How do you get this result roughly?
Oh, you have to be careful how So you have to study these operators, delta H's inside some correlation functions. And you have to be very careful about how the singularity structures are near the origin.
It seems like quite a universal result, right? So it will be a simple way.
Yeah, I agree.
I mean, what I thought you would say is that you would just take the.
Oh, for the stress tensor, I will take conformal transformations, which I will mention in a moment. But for more general perturbations, you have to, the only thing we can do is to study correlation functions and study how they behave when I try to do some integral, which I'll show later. There is a formula that relates this delta H with delta rho that I'll discuss. So when you try to, perform some modular time integral, then you have to be careful with near origin singularity. Sorry.
No, I was going to say that maybe what you do is you take the integral you had, integrated operator, forget about everything to the left and right. Just keep up
Exactly. That will precisely give this, and then the rest will give the point.
And then just expand out the density and take a long. Then expand out the density matrix, make it long and right now.
Expand the density matrix. What do you mean expanded density?
Meaning like the initial stage of the vacuum density.
Yes.
Now you have this small perturbation acting.
Yeah.
So that means that it's
Yeah.
you have to just perturbatively expand out.
So, okay, maybe that was your question. So, of course, with this perturbation series in mind, you have a formula between, let's say, first order in lambda between delta H and delta rho that I'll discuss. But then, for you have to calculate delta rho in terms of this ON. And then you cannot study that equation at the operator level. So you have to put the delta H inside a correlator with other operators. And that you can deal with and do the integral. And then you hope that from that correlator, you can extract the information of the operator back again. Maybe I can show you some slides later.
So the part that is not this delta H is just a unitary transformation.
Yeah.
And that unitary transformation, is it a unitary that extends across the whole thing, or is it bit by bit?
Yeah, so it's not right. I mean, so only for this sort of perturbations you have this, but if it's like GA tensor, GA bar, then there are no such factorization of it.
But even at first order and G,
Mm.
I thought somehow I was thinking that you've got this G. It's part of it is supported here, part of it is supported there, and this is the only part that is.
That's how we decomposed it. In the next slide, if you have the next slide, if you go, you have that is the delta H is equal to delta H commutative. That's coming from the separate part because that's a conjugate action, right, by U. So that translates commutative at first order, and then there is a genuine part.
So it's only a delta H that changes the entanglement entropy, for instance.
It's only that. So the commutative part will not change that. Will not change eigenvalues.
Thank you.
Okay, so yeah, I'm actually hesitant to go through this next two slides, but so I'll do it very quickly.
We don't have strict time limits, that.
Well, I still have lots to do. So this is actually simple, so it won't take any time whatsoever. So, for any subregion, actually, there's one nice thing about this vacuum state modular Hamiltonian. From any U to V, you can write the vacuum state modular Hamiltonian like this. And then, if you consider perturbations of this sort, which I was considering before, that will essentially be studied from this H naught by doing a linearized perturbation of this kind.
Sorry, what is the first line?
This is
H modular Hamiltonian.
for the vacuum state. It's this zero.
So that is whatever it is, right? What's with the subscript U and V?
Oh, this UV is the for some subregion U to V. So for Dindler, it will be U equal to 0.
Yes.
And so this is something that for finite subregion, not just semi-infinite, you can do. And then this sort of perturbation. So this is just very special. I mean, you have to essentially use some formula between delta H and delta rho later on for other perturbation. But just to give you an idea that indeed this endpoint contribution comes, I'm giving you this example. So this sort of perturbation can be implemented by doing conformal transformation of this kind, first order in lambda, into this formula. And you get something like this. And that you can then just expand order by order in lambda. And to first order in lambda, you get this expression containing 4 terms. The first 2 terms, you can check that it is indeed the commutator contribution. However, the last 2 lines, they vanish if the support function f were 0 at the end. So these are in fact the endpoint contributions, and you can check that if u is 0 and v is infinity, you indeed get back this NX operator that I discussed before in the context of stress tensor perturbation. Okay.
Sorry, one thing here I didn't understand. So we had this particular Hamiltonian for the vacuum state.
Yeah.
In particular region UV, right? And now you change that region.
Yeah.
What did you do? You have this G of Z, which is Z plus lambda of F of Z.
Yes.
And that we think of that as a perturbation.
Yeah. If there is some arbitrary function, GZ is some arbitrary
Oh, I see. That's the
conformal.
perturbation from Z, I see.
Yeah.
Okay, the first order.
Yeah.
Huh.
So I just expanded
Got it.
everything here up to first order.
Yeah. So it's just a while transformation on the same state, right? And you're looking at how that changes.
Yeah. In fact, you can show that if this G of Z is SL2R, then get back nothing. I mean, this entire thing cancels out and it is 0. So for global part, there is no change in the modular.
It's like this while transformation changes the relative lengths of the two sides. If you have a circle and you have one interval, the while transformation changes the relative lengths.
Yeah.
That's why it changes this.
Is it true that if I take now the vacuum expression when on that delta H, the commutator part will vanish, but the endpoint contribution will survive? Is it true?
We studied that, right? At some point, we had some.
Consistent with what Omkar said, right? Because the first order perturbation, he says the expectation value should match.
Can you say again what is the issue, sir?
From the endpoint contribution, maybe there will be something non-trivial.
Omkar said that it should match.
What expectation value of one is?
With delta H with respect to the vacuum.
Yes. Yes, that's true.
That should match.
Like for instance, the Yannick operator has actually.
Yeah, but it's not showing up.
Why? He just, I think you're saying, he's saying that the first order change in the vacuum modular modular is the Yannick operator.
Yeah.
It's expectation value in the random state.
Oh, the full thing is like.
No.
First order. First order.
This will be in it. This part will be in it. This is the commutator. Okay, so let's go to this formal expression that we have to use in future. So you start with some in the Schmidt basis this
Yeah, so here it's clear how you got this, right? Because your thought of this perturbation as actually symmetry transformation that you could do only because it was coupled to T.
Yeah.
But you previously flashed an expression which is very general.
Oh yeah,
Right.
yeah, that will come from these sort of expressions that I'll discuss.
Okay.
So yeah, so you need a more generic expression, and this was done by you have these expressions of rho A and rho A bar for the vacuum state, and similarly for the rho A psi if you excite this state by e to the minus I lambda g, let's say. And then if you assume that this G is GA tensor GA bar, which is the non-trivial case, then you can show that the change in the density matrix from the vacuum value will be given by this expression. Actually, it's a commutator. The general expression is this at any order n. It's a commutator between GA and this operator rho A bar 0 to the half GA bar tilde rho A 0 to the half. So this derivation, okay, there is a derivation of that. I'm not going through it. This GA bar tilde is essentially the mirror operator to GA bar. And for Ringler subregion, it's essentially this GA bar with modular conjugation by CPTJ. So GA bar is an operator in the A bar region, but GA bar tilde is an operator in the A region. So as a result, everything that appears on the right hand side is an operator in the A region, like delta. So now all you have to do, you have this delta rho A expression, and of course there is a series expansion between delta H and delta rho A. There is a law.
You're getting that delta rho A.
Yeah, you have to write rho A 0, rho A psi. You can consider them in some, inside some states, and then you can just subtract and find this out. There is a. You have to use this relation at some point. Yeah, it's this CPT, this modular conjugation. It also appears in this Tomita Takasaki theory, right? Relation between modular operator, Tomita operator. Yeah, I don't know if there is a quick way of seeing that this will be delta rho A. There isn't, I think. We have to derive.
So basically, when you say expand rho, how I mean, concrete is this object to expand? And this is what I'm not able to understand. Missing something simple, I think. What do you mean expand rho A?
Oh, so there will be some e to the minus I lambda g factor, right?
Uh-huh.
From both sides.
Okay.
So you have to expand. So essentially, this is the order lambda piece of rho S.
And what is GA? That bracket means GA evaluated all of them.
Which bracket?
Yeah, there.
This
GA,
one?
or that's just a bracket. Is that an argument of GA or?
So, oh yeah, G sub A, this one.
Yeah, and the next after that is the argument of that or just a times?
Times.
Times, okay.
Yeah, times. Yeah. So GA times rho A 0 to the. Okay. So yeah, so this is some formal expression that you can write down in first order in lambda. Well, you can also write down in any order. Saraswati Gaji did that. But we are interested only in first order. So in first order, there is a connection between this delta H and delta rho A. So what you can do is you can plug in the expression of delta rho A that we had in the last slide. And in terms of operators, modular float operators, ONS, I also had this formula in one of my previous slides. You can write down delta HA in terms of these G's. So essentially, this boxed formula is what is the formula that we'll always use. So we'll always consider some perturbation G written in terms of GA tensor GA bar, in which case the delta rho A takes this form. And we'll plug that delta rho A in this formula, which is simply by expanding this log. Nice representation. And this will just immediately give you this. So
in the case of this integrated thing, like integral of sig f times over, what is the analog of what is G and G?
right. So this we took to be, so when we did the example of spacelike slice, we took GA to be from 0 to infinity and the other one from 0 to minus infinity. And then, but when you actually do this integral, you have to do it like step by step. You have to take from, let's say, some minus b to minus epsilon, then minus epsilon to plus epsilon, epsilon to some plus a.
Right. Is it right that ON is D tensor legal? D tensor, right?
Yeah.
A is tensor. So yeah, so how do you write GA in terms of O? I mean, maybe it's not about at the end of the day, maybe everything organized.
Yeah, so there are actually two ways of doing it. You can even do it. In fact, that's how we did it. The formula I showed, you can take even G to be GA plus GA bar.
Okay, you're going to take it to GA plus GA bar.
However, I will be very careful near the origin. Or the second way is that you write whatever operator you are perturbing it with, although it's very difficult to do for arbitrary modular wedge. But for stress tensor perturbation and scalar perturbations, you can do it. You can write this O in terms of some O on the left side times O on the right side. And that will give you what is GA and GA bar. So anything that has support on the left side from 0 to, let's say, whatever, minus B or something, that will be your GA bar.
Yeah.
And 0 to A will be GA. So two special cases. Let's say GA is identity. So all the perturbations is in the A bar region. Then from that formula, the box formula I had, you immediately see that it's C. Because this GA S minus I pi S plus I pi, they cancel out. By the way, so I should mention that all the subtleties in fact come from here. The fact that you are taking these operators and modular flowing it to by some complex modular time. Okay, that is a subtle thing to do, which will come back and haunt us later. Okay,
That's usually not even verified.
that's actually for even for bounded operators, I think you can only do it less than IPy. So yeah, we'll talk about it. But you can actually consider these operators in correlation functions, and if you are careful with what happens at IPy, then you can extract some information out of them. Okay. And whereas if the entire perturbation is on A side, so GA bar is identity, then you can do some contour gymnastics. You can show that delta HA is a commutator contribution, and this makes sense, right? So this is the left hand side is change in the modular Hamiltonian for the A region. So if the perturbation is in entirely A bar region, it's 0. If the perturbation is entirely in A region, then it's a commutator as expected. And with more general space-like and null perturbations, we can recover the results mentioned before, but unfortunately, I don't intend to discuss that right away. Okay, what I want to talk about is this part, that there is a future wedge perturbation by a local operator in CFT2. You can also have some local operator inserted in the past wedge, but the analysis is similar. And as I was saying before also, that due to this imaginary modular flow, so this boxed equation is the same boxed equation we had before. We need to work inside correlators. So
one way to think about it is maybe that GA should be nice enough that S minus I prime makes sense.
Nice enough meaning
it should have some boundedness in modular images.
Well, we can still work with that actually. But the situation should get better with a better support function, suitably chosen support function. So we'll be using light cone coordinates. This will be my definition of light cone coordinates I plus and xi minus. So I plus positive this way, xi minus positive this way. And I can this local operator that I'll perturbing it with, I will call it O2 of some modular weight n. And effectively, I can, or at least for CFT2, because the correlators factorize, I can write it as the left moving part times the right moving part. So it's like this, where the left moving part I can think of GA and the right moving part I can think of GA bar. So you remember in deriving this formula from the Sarkar formula, I had to take G to be GA tensor GA bar. So for these perturbations, effectively, GA is this and GA bar is this with this sort of conformal dimensions and modular weight, left moving, right moving weights. And we have to work inside correlators. In particular, we have to work inside Weismann correlators. So the prescription for tackling the divergence of Weismann correlators will be, you put an I epsilon to all the times that appear in these operators, and the I epsilons of the leftmost operators are the biggest. So you have this ordering, right? So the leftmost is the biggest, then greater than the next one and the next one.
So what is the meaning of this equation? G is equal to ON, that is just the local operator, I guess, right?
Yeah, so this is the operator I'm perturbing it with, and I'm saying that for CFT2, effectively because the correlators will factorize, in effect, I can treat this as some OL left moving times the right moving piece, where I can think of this OL to be an operator in the A region, and OA bar to be the operator in the A bar region. So this will be this is why I'm identifying this OL as GA and OR as GA. And I can sort of use this form.
In what sense that OA is in the left region?
Yeah, so it's just have, dependence on pluses. So it is
Go at that point.
just exactly for the
Okay.
Okay, so this will be the Whiteman prescription, and let me also mention the second bracket. So this second bracket means that I can have these two operators in whichever order I want. So it can be O1, O2. So whenever I'm saying O1, I mean O at xi1 plus xi1 minus O2 will be xi2 plus xi2. So O1, O2 or O2, O1, both are described by the same equation. It's just that for O1, O2, epsilon 1, 2 is positive, and for O2, O1, the expression is the same, but epsilon 1 is not.
So could you just explain, maybe you said this a bit, what do you mean by future perturbations by local operators here? What does that mean?
Yeah, I simply mean that, the G I had before, this G is just an operator.
So you're still inserting it at t equals 0?
No.
No. But I thought you were computing something about the slice at t equals 0.
That was before.
Oh, so now
Yeah. Now I'm doing something. This is the case 2.
Uh-huh.
I did not actually, I'm sorry for that, but I did not discuss case 1. This was the case where you had, that result.
It's no problem. Can you just tell me when you put this future operator, what slice are you computing your?
Sorry.
You're still computing it at the t equals 0 slice. It's just that the operator that you're perturbing that state with.
Yes, so understand it as
It's the operator which would have evolved to this.
Yeah. But then you can also, as you said, you can think of it as a back evolve. If you back evolve,
Yeah.
think of it as a Heisenberg operator, like that equals to some product of nothing there.
So then if it's like finite time separated in this case, these will be finitely.
Yeah.
So there'll be no delta H. No funny stuff.
No, but it's not.
No, but still G is G a tensor, G a bar. So you will have funny stuff.
Well, sorry, if you've got something at finite time separation and you really have propagation backwards, 45 degrees, then there's no support on the origin.
Yeah, so there won't be endpoint contribution.
There won't be, yeah.
Won't be, but there will be other issues.
No, but
It is still not commuted.
All this is happening big.
But say we were doing the first order,
Okay, sure.
Yeah, we are going to first order.
then it's one thing there and one thing there.
That's
separate, right?
Separated,
It's
but it's still not U factorizing.
It's not the operator is not this times this, right? It's 1 plus this times this.
1 plus this.
Operator is not. Oh, I see.
It's in the exponent, right?
It's in the exponent. Yeah, so U is still not U a tensor, U a bar. But it's not, it's true there won't be
But
endpoint.
still, there'll be nothing at the origin.
But
Indeed.
but it's not a local unitary.
A local unitary would have been 1 plus this plus that.
Yeah.
So 1 plus this times that.
I see.
And also, these are not unitary. G is some. Well, no, but as you said, it would be Hermitian plus Hermitian. 1 plus Hermitian here plus Hermitian there.
Yeah.
But it's 1 plus Hermitian here times Hermitian.
Indeed.
I see. So it's not product of two unitaries.
Yeah.
I see.
Okay, so in fact, for this GA and GA bar, if you plug in this formula, what you can show is that formula boils down to this formula. So let me just spend a little bit of time explaining. So first of all, I have changed this S variable to this W variable. And what we have also done is, remember we had this S minus I pi, S plus I pi's. So we have regulated them.
So what is this I epsilon prescription?
Oh yeah, so this is this Whiteman I epsilon restriction where you have the leftmost time gets the biggest minus I epsilon. OT1, OT2.
Is this some particular ordering prescription?
Well, yes, I mean, the I epsilon depends on the order. the sign of the epsilon.
Nice.
So this is why I use these braces here, because I would be at some point interested in both O1, O2 and also O2, O1. And I will just be careful with the signs of epsilon 1.
Sorry, so just about the previous discussion. So, the important thing seems to be that the operator that was local in the future evolves to something non-local past. And that's why it has this funny nature.
Exactly. Yeah.
So,
Because the subregions are right and left.
yeah, so it's a convenient way of parameterizing non-local deformations.
Yes.
It's
Yes.
because it's local in the future.
Yes.
Double trace vector.
Yeah. Double trace with 1 year.
Yes.
What if it was in the past rather than in the future?
It will actually go, the analysts I'm going to show, it will go through.
Sorry, but so far you were talking about operator expression, right? Like either this, like delta is some operator. Like now you're going to look at some correlation.
Exactly.
Okay, that's
Now
what
I
you're
will.
talking about,
Now I will.
operator ordering.
Yes. So yeah, this is what I was mentioning here, that due to imaginary modular flow, actually we need to work inside correlators, and I'll be using Whiteman correlators with these epsilon prescriptions. Okay, so what I did here was related to the box equation. Compared to the box equation is that I have introduced this regulator e to the IR or e to the minus IR for S goes from 0 to, so S was taking the value I pi, so this R in the W coordinate, it goes from, it's actually R equal to pi, but we don't want to put pi right away. We want to go from 0 to pi in a controlled manner. And in fact, you see it that for when R was 0, meaning if the imaginary pieces are not there, then these operators are in fact all on the right wedge, as it should be, because you are trying to calculate delta H. Because you see, xi2 plus is positive and xi2 minus is negative, right? Because it was future inserted here. So xi2 plus is positive, but xi2 minus is negative.
So where is this formula coming?
This formula is essentially this box formula where I have put the value of G and G1.
What about the tildes?
Yeah, so the tildes are related to, there is a formula for tildes, did I not write? So it's this J, G, J, and then it can be related to back to G.
But this is quadratic in G then, right? Each term. But here,
Yeah, so what we did is that we wrote things in terms of OL and OR, and then you can combine them together. Just like I wrote here to here, you can go from here to here.
oh, I see.
Yeah. So that's why I wrote everything at the end in terms of
I see. As non-random.
yeah. So what I was saying is that if the imaginary parts were not there, then you see this is positive and this is also positive. So it's a right wedge operator because W is positive, xi2 minus is negative. And similarly here. So it's a right wedge operator. But if R equal to pi you put right away, then you see this becomes an operator in the past wedge. And that is what you of course don't expect because they are trying to calculate delta H. So that also is like the first sign that you cannot just put R equal to pi right away. But what seems to do the trick is that if you put in a regulator and you take 0 to pi in a control manner, rather pi minus delta, and then take delta going to 0. So we'll come back to, of course, this issue later.
So it's an embarrassing question, but HA is just the modular Hamiltonian for the right part.
Yeah.
And at some point you said you will only deal with HA minus HA bar.
Right.
But here you're.
Yes, here we cannot directly look at actually delta HA minus delta. We'll first look at delta HA similarly to delta HA bar and subtract and hope for the best.
And here maybe that's okay because you don't have anything at the origin.
Well, even when we had things in the origin, you can do that. As long as you are careful near the origin.
Okay.
Yeah, so it's indeed, I said in the beginning that I should not think of delta H bar separately, but for operational purposes, you have to do that. Yeah. So we'll need to deal with, so we will put this delta H of this form inside correlators. So we'll study both 2-point and 3-point correlators. Actually, 2-point correlators are not enough for reasons I'll mention. And there will be several divergences as you have in a QFT correlators. And we'll see that a particular prescription is necessary, especially in higher than 2-point functions. In particular, what you need to do is you need to set I delta to 0 slower than I epsilon. So you have to put I epsilon to 0 first, and then you have to take I delta to 0. Delta being this regulator. And as we will see, I mean, this is probably a statement I should not have written here, is that it has to do with various poles and cuts that you have in the correlator to pinch the contour, this W contour, in an unambiguous way. You will see what I mean by that.
Sorry, correlator, sorry.
Yeah.
What correlator are you talking about?
Yeah, I'm talking about putting this delta HA with another spectator operator, like let's say O. So O delta H. So all I have to deal with is like O1, O2, because delta H has this O2. This has this O2.
And you're interested in this correlator for what purpose, please?
Because I don't know what to do with this operator expression. So what our point of view will be that also, these delta H's are bad operators particularly, but they make sense inside correlators. These are something called, I think, sesquilinear forms or something.
So you're going to use this delta HA to see how this change in density matrix, it implies change in correlators.
And then try to, do all these integrals and so on, and hope to extract delta HA back from it.
So now, if you're only interested in the correlator, you could just compute the correlator.
Yeah, but even there are some subtleties which I'll discuss. You have to have subtleties, you will have subtleties near this delta equal to 0.
Sorry, the correlator itself would be just some correlator in the conformal field.
Yes. The CFT correlators, but no, but
some spectator operator, and you're changing the state by putting another operator. So either that and this, or maybe a 3-point function that is behind.
So as long as you are away from the divergences, you can just compute it. But there are some subtleties regarding tackling the divergences.
And these divergences have to do with the fact that you're not looking at time-ordered correlators. I mean, time-ordered correlators.
That has to do with the fact that there will be new types of singularities when you calculate delta H O2, O1 delta H or delta H O1. Those new singularities will have some ambiguities that cannot just be resolved by Whiteman. So there will be various poles in the correlator. Let's say if you choose your conformal dimensions appropriately, which you will do, and those poles can collide, and they can collide in an unambiguous manner.
So in the end, you're computing some 2-point function of spectator operator.
We'll do 2 and 3.
Let's say 2-point function of a spectator operator in a given state. Right?
In a given vacuum state. Yes.
So that you could create the state by operator insertion, create the bra by operator insertion, and you have your 2-point function.
Yes.
So then this would in the end be a 4-point function in just the undeformed 3FT.
No, not 4-point function. 2-point function. We'll only consider delta H O.
I think what I'm saying is that one expects delta H to be a good Lorentzian operator. That's an expectation, right?
Delta H.
Yeah, delta H. Actually, H till H, that double F, the full modular.
Yes.
Okay, let me ignore the subtleties coming from the UV issues. One expects delta HA to be, let's say, a good Lorentzian operator.
Yeah.
And therefore, its correlation functions in good states should be fine.
Perfect.
To me, that it should make sense. But he seems to be finding some.
I mean, what I'm trying to say that it makes sense at the end of the day, but you have to be,
I think, Chirag, maybe the issue is that what you said affects the entire state, right? And then the correlation that you're computing is with the A and A bar piece both. I think here he's just computing with A. Delta HA and O, right? What you said with this.
But if I just put 2 operators just in the A region, that should be the same thing.
No, one operator is playing the role of changing the state, right? And then we are probing that.
Ah.
The change in the density matrix.
Good. So say I put my operator that changes the state, yeah?
Yeah.
I put another one in the past. So now I've got expectation value in this change state. Then I can compute my correlation function just in the end.
No, but it would still be in the state that is the full state, right?
Full state, but since I'm only computing something in the A region, what doesn't matter?
No, but you may not get the exact correlator he's computing, right?
Why not?
Because your HA, so your rho is e to the minus HA itself.
Yes.
Let's work in that process.
Yes.
So then when you do the perturbation, you will get a delta HA integrated value. You don't know. Can I write a formula? Rho A is like e to the minus HA, and then HA is like H naught A plus delta HA. So if you put this in here and expand out, you will get you see, you have to, right? You're gonna mess up the signs. Something like this. Okay. So you'll get some integrated correlator of delta HA. Not the thing. He wants to literally compute.
Oh, you compute the local thing.
Yeah.
He wants to compute the local thing.
Yeah.
I see. I see. Now I understand. You're saying it's not just in the state.
It may not. I mean, maybe there's some way to extract.
I see. Now I understand.
Yes.
So this cost is supposed to, all this integral is supposed to do that, right?
Yeah, the integral is supposed to like extract the delta HA
from delta rho. So this had origin in the original log expansion.
That's right.
So in this particular case, isn't that HA just localized at one point?
This one?
This back evolution.
Yes. So, but delta HA is changed here. And the perturbation, unfortunately, is not just ON.
But I get it. Yeah.
Yeah.
But I mean, is it right that the expectation is that delta HA is equal to length of it? And somehow you're seeing divergences, so that's bad, right?
The correlators can make sense.
Oh, so you're saying that actually there are.
Yeah. Well, there are divergences, but the divergences must be dealt with carefully. Near delta going to, yeah, I'll discuss here. So what I was saying here, what I mean is essentially we boil down to this point. There will be various poles, let's say. You may also have cuts, but let's only stick to poles. And these there will be singularities. The divergences will come when there will be one type of pole hitting the other type of poles. I'll discuss them. So, and then you have to make sure that you know precisely from which direction they're hitting the pole. So there is a subtlety like that. So we will be then led to this sort of limit. We'll start with non-singular operator configuration first, and then we'll move to resolving the singularities. And
sorry, this I times R that you introduced, that was the regular.
Yeah, so this would have been e to the minus I pi because you had this s minus I pi. So in W coordinates, it would have been e to the minus I pi.
And is it possible to draw a picture to? So this is some local operator, not this one, the next.
Yeah.
This is some local operator, right?
Yes, but with arguments here.
Correct. So it's some integrated.
Yes. Well, yeah, I mean, there is even if you forget about this integral, this R, you don't want to just put pi right away, but rather you want to track how things move as you go from 0 to pi.
Sorry, what was pi? Pi was what?
Pi was this thing that came because you had in the Sarasyu-Gaussian
going from one side to the other. That's a pi.
Yeah. So this rho 0 to the minus half factors that just comes. That means that you are doing some imaginary.
You're doing angular evolution in Euclidean space, right? things.
Yeah.
One side. I see.
Indeed.
I see.
But this is the kind of thing that's worrying, right? Because you expected delta H to be a good
That's
operator on one side.
I
So
agree.
now why are you going to?
Exactly. Yeah. And indeed, you see that as you put r equal to pi, you get a past wedge operator, right? That's what I said. That if you just put r equal to pi, it's an operator on the past wedge. So you cannot just do that.
What do you mean past?
Meaning, so initially your operator O was what at some positive xi2 plus negative xi2 minus because it was on the future wedge. But now if you just put r equal to pi, it becomes a past wedge.
Let me ask you a very stupid question. Suppose you have this thing and I really take this 45-degree line seriously. I would have expected that in this right side, your H was supported at just one. That is wrong.
That is wrong because this G is not GA plus GA. So U does not factorize.
Right. You're saying it was something here and something there. And that something there is this pi.
Yes.
I see.
Well, it's somehow imprinted there.
Yeah.
But then, I mean, it should be done in a clever way such that you get only an operator on P.
Yes.
That's
So
the imprint of that thing over there.
Yes. So you have to, So this delta HA for r equals to 0, it was correctly a right wedge operator. But then Sarasugajin formula tells you to do an I pi or pi rotation. At pi, if you just put it, it's a past wedge operator,
Which doesn't make sense.
which doesn't make sense. So you have to track it in such a way that it remains right wedge operator.
Is this like the Papadudimas Raju mirror operator?
This one is this GA bar tilde that
What they did, they said, I've got a very complicated operator here, and that's represented by a simple operator here. So isn't this like the mirror operator corresponding to the simple insertion?
that's where the comparison ends. But I don't know if they have studied these subtleties before.
I don't know. I'm not saying that I'm not saying they've done it. I'm just trying to understand roughly. So what you're doing is creating the same thing as inserting something on this side by inserting on this side, and you can do that because of the high entanglement of the two sides. Exactly as they
Indeed. Okay. And we will find out that when we calculate correlators, they have well-behaved value. I mean, it's not diverging and w equal to 0 and infinity. And we will take the left-right conformal dimensions in such a way that when we study the correlators, 3-point correlators, we'll only have poles and no cuts. Okay, so let me go to these some particular value. So let's say I put an operator, a spectator operator on the left. So whenever I have a superscript bracket L or R, that will mean left wedge operator. Then you can use those Whiteman correlators. I showed
It was on the right.
right. Delta H was right.
That's right. But suppose now I didn't want to put everything to the right. I was going to allow myself to work on left and right.
Mm-hmm.
Then everything would be very simple. Then your correlation function computation.
For non-singular configuration, it will be very similar. In fact, this is that.
Okay.
So you can forget about all the epsilons. So let me come to this. So OL delta HA, it will look like this with my previous slide's expression of delta HA, and O is some operator which is on the left way, so xi1 plus xi1 minus both are negative. You can just use the Whiteman correlators with the correct epsilon prescriptions this way. And then you see there are a bunch of poles. There is a pole at w equal to -1, which I'll call w0. And there will be some poles which are mobile poles. That's what I'm calling Wm. And there will be a mobile pole coming from this term, which I'll call Wm minus. It looks like this. It is mobile because as you take r from 0 to pi minus delta, it moves. And then from this term, there is another mobile pole. It has the same expression as the Wm minus, but it's only with terms with a plus IR. And then there are fixed poles coming from these terms, which I will call W.
Right, and technically, I should also probably have another operator, right? Because you should be looking at matrix elements of delta H. So is it?
You mean
is it-
3-point?
Yeah.
Yeah, we'll come to
Yeah.
that. Yeah.
It's not so important.
No, it is very
Oh,
important.
it is.
It is very, yeah. So, and I will mention why that is very. So then what you have that from the first term, as r goes from 0 to pi, you have this one of the mobile poles. It will rotate like this and drag the contour down. And the other term, it will rotate counterclockwise. Counterclockwise. And this will actually always happen in delta H. Okay, the first term of delta H that comes from, and please remember this, which comes from this first term. The corresponding pole will always rotate clockwise, and in the second term, it will always rotate counterclockwise. And ultimately, we will get for this OL delta H a contour which is surrounded by a counterclockwise contour, a pole which is surrounded by a counterclockwise contour right here. But you can also take operators in other wedges, either on the right of the delta H or left of the delta H. And if you could have forgotten about all the epsilons, which I can do because I'm only considering non-singular configurations, then the final result of O delta H with braces, because remember with braces means it can be either right or left, is actually given by this pole surrounded by a counterclockwise contour and this thing integrated. Okay? So this will always happen. So this is just one example when O was on the left wedge and on the left of the correlator, but this happens more generally, no matter where O is and no matter where in the correlator O is. Okay, so this is the general formula. This contour will always be encircled, this pole will always be encircled by a counterclockwise.
Sorry, I've stopped following the details, but one quick question. Suppose I didn't have this delta. So what you've done is take this delta H and represented everything on the right.
Yes.
But suppose I wrote delta H as left change times right change, and then did the computation. Would I get the same answer?
No, I mean that's
what you've done.
What this formula is.
Yeah. Right. Yeah. Right. But why from that? And so that computation then is just straightforward, right? I mean, from
Yeah. I mean, which computation? This computation?
No, I was thinking you had some singularities and so on here.
That I will come to later.
But if I represent it as this times this, you still have singularity?
Yes.
Nice.
So we had this this OL times OR.
Yeah.
So when I put these OLs OR back in here, then I can write everything again back in terms of this O2. So this was what I was also telling Abhijit. So these O's actually have both OL and OR.
Nice.
But now that I have O, in the delta HAO1 correlator, I can use the OO1 correlator and I can write them like this. Okay. So this result, you can just compute some residue and some results are there. Okay. Similarly, for a 3-point function, you can start with this 3-point function. Again, I'm only considering non-singular configurations, meaning once I will write the correlator, I'll write all the poles. I can safely ignore all the epsilons. Then you will see that there are more poles. In fact, there will be 2 mobile poles for 3-point functions.
So mobile is this I pi rotation?
Yes, as r goes from 0 to pi.
Nice.
And 2 of them will be then there compared to 1 for the case. By 1, I mean like it's still starting from here, it's just going 2 different ways. So I'm calling them 1.
So
but
this is what Shiraz was saying. I'm struggling to have why what you're proposing the same calculation as this. Where you do this, just change the state by its operator and you can model it like so and then just compute the correlate in that state. As opposed to computing delta H, just looking at the delta H for a region and then computing the correlator with that. Why are these the same?
I thought what your delta H was a deformation here times deformation here. And then I thought what you were doing was implementing this deformation here on this side.
No, but what she's computing here is correlation function with delta HA only, right? Not with this other part also included.
But delta HA, which includes the effect of this having changed, right?
But whatever it is, it's still delta HA.
Right. But I thought it was exactly just taking what this double insertion and rewriting it as an operator on this.
It does have the effect of that, but it's still not what delta HA bar. I guess there is not.
What you are saying is perhaps delta HA plus delta HA bar.
No, I was saying times this times this. I was thinking that the coder, as far I was thinking in the language of Debajyoti Sarkar, that they have this insertion, they can exactly implement the same thing by putting another insertion on this side. The product of this times something else. I thought that's what he was doing. Effectively, right? Or not? If
It is. I mean, I have the effects of the OR as well from A bar. I do have the effect.
and that, in the end, what you're doing is a computation which effectively inserts it on the right? Isn't this pi rotation?
Indeed. Yeah. So GA bar tilde is indeed an operator on the right. So everything on this side should be an operator on the right.
I mean, so I think maybe conceptually it's right.
But not technically.
I mean, technically, it's not just like it's not just what the operator that perturbs the state is, right? Then you have to figure out the density matrix from that. You have to take the log of that. So
Sure, but
after that, after all of that, I mean, you get some operator, and at least, conceptually, I think what you said makes sense.
Sorry, I mean this delta HA, this correlator that you are computing in which state? The vacuum state. Vacuum state. So this operator is only supported on the right side. Right?
Delta HA?
Delta HA.
It should be, yes.
Right, and then you are probing it by inserting operators anywhere you want.
Yes.
Now, but what Shiraz is saying is true. Then it was actually the state it changed, where on the left as well as the right. So you should see singularities even if the operator goes on the left side. That is not what you would see, right? There will not be any singularity on the left side because the delta H is just supported only on the right. How can there be singularity on the left? Is this correct?
There will be some weird singularities which I'll mention in a moment.
That doesn't sound good because delta H it makes sense at all as an operator on the right.
So let's see what the singularity structures are.
So can you explain what those two terms are like physically? The term in the bracket.
Here.
Yeah.
Yeah, so this is the operator you partnered with. But Sarkar formula, this log expansion, tells you that when using this operator you are trying to write delta H, these operators must be modular evolved by some imaginary modular time.
And the second term is like
Yeah, so there are it's just a technical issue that there are like two terms that comes, in fact. We had this derivation. I mean, it's not Sarkar formula is, let me just go back. This formula. So it just happens to be two terms. So
because of the commutator.
well, the delta rho just happens to be of the form of a commutator. So it's just there are two terms which you put in the Sarkar formula. So there are two terms. So delta HA, Onkar, I mean, it definitely has to be a right wedge operator, but let's see its divergences, especially in the 3-point functions where the divergence structure is richer.
But before that, just 2-point function.
Yes.
Where are the singularities?
I will mention. Yeah. So I unfortunately did not write the final expression, but I'll at least tell you about the singularities. So let me discuss the 3-point singularities and tell you which singularities are not there. So if you look at these expressions, you see that the singularity is coming from, this xi1 3, xi1 2, but then xi2 3 and so on. But then
what is 2 xi2 etc.?
Sorry. So my
to be integrated over.
Yeah. So the perturbation of perturbing operator I will always call O2. This I will always call O2 and its arguments will always be xi2.
Right.
And the spectator operators I will call O1 and O3.
Right.
For 3-point, and they will be at xi1 and xi3.
Right. And xi2 is still some particular.
Xi2 is always with particular sign.
That's fine. So
but these can change.
Yes.
Right, so but now you see there are these extra singularities in this correlator. Just happens to be if you just compute. And these correlators are these singularities are at these values. So let me do a pictorial representation. So you have O2 here. So of course O2, O3 divergence is there if they are like separated, the usual light cone divergence also with O1, O2. But then there are these extra singularities when O2 and O3 falls on this hyperbola. So this is, for example, this term. Xi2 plus Xi2 minus Xi3 plus Xi3. These extra divergences are also there in the correlator.
First of all, how can there be over O2 divergence?
Well, if you have, because O2 is on the future, if O1 is on the left.
But that's not what you're computing. You're not computing correlators of O1, O2, O3. You're computing the correlators of O1, O3 with H.
No, but delta H has O2, right?
It has O2, but
Yes.
it is delta H. I thought the whole point is that it is not O2.
Yes.
So then how can there be a delta H, as you say, supported on the right side? So let's just erase that delta O2 and just write it as a line wherever it is, whatever it is, it's on the right side. With that picture, how is it that O1 will have similarity with O2?
So let's just take the formula that we are given with, where O2 is clearly a future wedge operator. So in the QFT correlator like O1, O2, O3, there will be these divergences, and that's what we are finding. Now, of course, delta HA should still make sense as a right operator, algebra operator. And we will see that even with all these correlator structure, how does that happen?
So you're going to show how this O1 or divergence goes away. Right? Right, I thought you said.
Well, this delta HA will be an operator on the right wedge in the sense that it will satisfy the correct automorphism. It will keep the operators of the A side as an operator on the A side.
Therefore, there should be no branch cut between O1 and for O1, right? No branch cuts on one side.
Indeed, so there will be some I epsilons which will be missing. So let me come to that. So we'll have a very precise.
So I'm saying this picture, everything should be understandable through this picture. This is the chicken typing. Whatever it is, may complicated, maybe there is something special happening here, but
Nothing should happen.
Right. So now O1, your O1 is here,
Yeah.
is here.
Yeah.
Every singularity should be consistent with this picture, right? Because finally this is what you're comparing.
Well,
Even though that O2 would suggest that there is singularity here.
yeah. But we'll tackle it in a slightly different way.
Right, we can tackle it, but finally is this correct expectation?
It is the correct expectation.
But is HA a well-defined operator?
Hmm?
Is HA a well-defined operator? Do you have to do the sewing of HA with HA?
Well, delta HA is not a well-defined operator, but its correlator should still be well. I think that's the statement.
The non-well-definedness has something to do with like very. I have an operator very, very far away on the left side. Then at least that should come in.
We will come back to this.
Yeah.
So indeed, the locality properties we will deal with by studying the commutators with this operator and delta HA, and we'll see that there is none. I mean, the commutator is. But if you just, and that's the interesting thing, if you are just working with Sarkar formula with a future wedge insertion, then it looks like there is a divergence. Okay. So these and then there are these also these even weirder divergences. So you take this O2 and it passes through this hyperbola. But let's say you have O1 and O3 in such a way that null lines coming from them, precisely crosses at a point on the hyperbola. Or the other way. So O1, O3, it's a mirror hyperbola here, and O1, O3 just happens to cross over here. So these are these singularities. Xi2 plus Xi2 minus Xi1 plus Xi3. and xi2 plus xi2 minus minus xi3 plus xi1. So they're precisely these singularities. In a 2-point function, you will only have this and that, the first two, but not the lower two.
Sorry, why the third and fourth diagrams would have non-zero contributions to 3-point correlators of O1 delta H O3? Because it's lying outside the light code, right?
Yeah, it's you are saying why there is this divergence.
Yes.
Yeah, let's see why, how to deal with them. But there is, I mean, you will still at the end of the day, delta H will still be an operator on the right. So there should not be, any weird divergence.
No, but even though, let's say I assume your take on the first diagram, let's say that O2, that delta H is coming from something from two light rays, from O2, let's say.
Yeah.
But for the third and fourth diagrams, the O2 is clearly out of these light pool, right?
Yeah, so in this figure, for example, but this figure can also change. I mean, they may cross even here. Well, not, yeah, even here. So this point would be on the left or could be on the right.
It would be far away as well.
Could be also far away indeed. Yeah. So one can check that these upper singularities, they can be resolved by the standard Whiteman-Epsilon prescription, and they actually come when these two mobile poles that we had, these two collide with each other, or one of the mobile poles collide with the W0 equal to -1 pole. However, these lower singularities come when the mobile poles, these WMs, they hit those one of those fixed poles WF that we showed, for example, for 2-point function, we had this one fixed pole. For 3-point function, you'll have two. So when this thing hits this thing, then these second two singularities will arise.
Why do you have two mobile poles rather than one?
What are mobile poles?
Yeah, so mobile poles are the ones that move as you take r from 0 to pi. They will move, right? Because we don't want to put r equal to pi right away. We want to keep a regulator. And we want to check, and you have to check that to correctly analyze this problem, that how do they pinch the cone? So to answer your question, for 3-point functions, you have two sets of mobile poles because you will have xi2, xi1, but also xi2, xi3.
So 1 and 3 are the insertions?
1 and 3 are the insertions. Yeah. So what you want is that, in let's say this is the W plane. So suppose you have a mobile pole starting here at r equal to 0, but at r equal to pi, it goes here. So this distance is governed by some I epsilon. And the contour is this from 0 to infinity. So it pinches the cone. But there could be in 3-point function, and it's not there in 2-point function, that there is a there is a fixed pole sitting here. So this mobile pole can hit this fixed pole. And that will give rise to this last two singularities. But you have to be pinching the contour in such a way that one pinches from above, another pinches from below. It's like the situation in the simple expression of z minus a, z minus b. So this thing has a contribution only if a and b are coming from either side.
I have a zero further question.
Yeah.
This O2.
O2, yes.
Used to
Yes.
the stage. Oh, sorry. That was in the exponent.
Yeah, that was in the exponent. Yes. But G comes, in the Sarasugajin formula in the main integrands.
What are you going to ask?
Sorry, I was starting to get worried that that was not in the experiment. Then it would make the state non-null. But
So we'll have some comments when it's not a local insertion, but also there's a support function.
okay.
Right. So what will happen in these cases for the 3-point function case is that, I keep saying that delta has to be much larger than epsilon. So if you do the other way, that is, you take delta to 0 first, you just put r equal to pi, let's say, and you keep epsilon non-zero, then you will end up with a situation, you did not follow this rotation at all. You end up with a situation where it seems both poles are down. Okay. So then you do not know whether you hit the contour from either side. So this to avoid this sort of ambiguity, but this sort of ambiguity will be in some terms. Because for example, you could have had a situation where instead of starting from here, the mobile pole, it starts from here. Because the I epsilon is negative, let's say. Okay, then even after pi rotation, even if you put delta equal to 0, it ends up on the top upper part of in the first quadrant. And then there is a fixed pole on the lower quadrant. So you know for sure that they are hitting from either side. But in these cases, it will be no ambiguity will be there. But in these cases, there will be an ambiguity if it starts for, let's say, for example, from. So because you have to kind of study it case by case, but you will finally realize that you have to take I epsilon to be 0 faster than I delta. And this is what I was also mentioning, but that these poles must pinch the contour in an unambiguous way from either side. So how to resolve these singularities? It takes a bit of analysis, but very simply, think of it like this. You rewrite this delta HA with r equal to pi minus delta. So it's now again this, I'm going back to this operator delta HA written in W's. So then you can expand those e to the minus IR to first order in delta, you will have an expression like this. And remember, the first term will always produce poles which are rotating clockwise. And you will indeed see that whenever a pole rotates clockwise and pinches the contour, that singularity will be resolved by xi2 going to xi2 plus I delta. Because I cannot put I delta to 0. I can put I epsilon to 0, but I have to keep this I delta. And similarly for the second term, the poles which will rotate counterclockwise and pinch the contour. So for example, you can have a situation where there is a mobile pole here and it is hitting the contour from below, and then there is a fixed pole right. So it's again a singularity of the last two kind. And then in those cases, the singularity will be resolved by some prescription, and then you will end up with some prescription here where you will see that the signs of I delta is actually correlated with sign of epsilon 2j. And it is because which way it is moving and from which direction it is hitting, that is really dependent on the sign of epsilon. So even though these are resolved by deltas only, and I will have more to say about that in a moment, which will probably be more clear, we will find that the resolutions of those ambiguous singularities will be done by this way. Okay? So it's very particular depending on where is the jk, which are the spectator operators, where are they located, whether their values are plus or minus, etc. Okay? And similarly for delta H bar. So if you use these contour prescriptions, these I delta prescriptions, then you can now write the 2-point functions, but with the correct I epsilons, which initially I put them to 0, and you will find that I have also taken some particular values of delta and n. Then you will find that you can just readily do the integrals. The results look like this. And once you have this correlator with delta H and delta H bar, then delta H correlator O will take this form. But in fact, you will realize that this is same correlator as delta H commutator times O. Okay. So in the 2-point function, it seems that even if you are very careful with all the rotations of the poles and resolutions of the singularities, the 2-point function of any spectator operator O with delta H is same as if calculating correlator of O with delta H commutator. So that would seem to suggest that at least as long as you are only talking about 2-point functions, delta H is just delta H commutator.
Delta H commutator is what exactly?
That minus I lambda H naught comma G, which you would have gotten if you were factorized.
So it's a commutator of original H with something.
Original H0 with the G, the G. That that came from Becker-Hausdorff formula. Yeah.
Right.
Yeah. This one. Which we spend so much time convincing ourselves that it should not be the case, and there should be some extra terms.
I thought that commutator formula made sense when the G was of the form GA plus.
Exactly. So even though G is now not GA plus GA bar and GA tensor GA bar, you get this. But the reason is the following, which I'll mention now. So this is only a simplified version of 2-point functions for 2-point functions. Okay, because this is only for 2-point functions. In higher point functions, you will have some contact terms coming from this I epsilon regulations if you do properly, but that contact term will annihilate the vacuum state from both sides. So this is why in 2-point functions they are not there. So what you rather have to study is focus on correlators, and that starts from 3-point onwards. But delta H is sandwiched between other operators and doesn't hit the vacuum directly.
At least that makes clear that singularity is not there, right? Because delta H commutator certainly won't have that singularity because that is only on this side.
But even in 3-point that will happen. Yeah. So don't be alarmed that in 2-point function delta H is delta H commutator. It is happening because you are calculating a very particular correlator where delta H is always hitting the vacuum state from one direction or the other.
So this is commutative with only the right part of the operator.
Yes. So here I have actually subtracted, and this is delta H. So it is minus I lambda H0 with the extended comma G, or was it G comma H0?
Right. So now this will have the full singularity.
Yeah, that is exactly the calculation that I would say, right? If we have both sides.
Yeah.
Okay. So you can use then these same I epsilon I delta resolutions and then calculate the 3-point functions that we obtained before, but now with proper I epsilons inserted. So you see, now it just requires some analysis, but you will get some epsilon 2-3 factors. This correlator is actually very special, where I have taken, because I will be using it later, this O operator on the left and another operator on the right. So I indeed have one here, and O2 here. And this O2 is giving rise to delta HA. And what it will have is it will have no factor of epsilon 1, 2. Okay. So here is where the magic will happen. So no epsilon 1, 2 will be present, but only epsilon 2, 3. If you follow that I epsilon, I delta prescription. These I epsilons are actually I deltas, which is because they are correlated with the signs of epsilon, I have written them as epsilon. But the point is that only I epsilon 2, 3s are appearing in the 3-point function and no I epsilon 1, 2. And that will help you with the vanishing of the commutator between O1 and delta H.
So this I epsilon I delta followed very well.
Yeah.
But is it that you had to make a choice at some point, or was this dictated by physics, the kind of prescription?
It was dictated by the resolution of the so I had 2 regulators. One is the Y prime I epsilon, which gives rise to all these commutators, and then there is this regulator I delta that is coming from complex flow, modular flow. Now what we saw by studying this, how it pinches the contour, we saw that to regulate some of those divergences in 3-point functions, you have to take I epsilon to 0 first and then I delta to 0.
I see, but is this not a conclusion that you can reach just by physical considerations?
At least we don't see how.
But I delta going to 0 is sort of like really implementing the mirror operation. So that delta is bigger than epsilon feels like the statement that the mirror operator is some approximation. Right? I mean, because delta is taking a full pi. Epsilon is in your definition of the operators, and delta is in the rotation. So the fact that delta is more fuzzy than pi, than epsilon, seems reasonable. Right? But this mirror is an approximate.
No, but the fact that the signs are correlated and such.
I don't know.
Yeah, I mean, you don't have to, okay, maybe there is some deeper understanding of why the signs are correlated, but the signs are indeed correlated, and that helps you see that there are no epsilon 1-2s.
And this delta was basically the phase of the contour.
Right.
So that you could have changed by deforming the contour. But you're saying that you can't deform the contour all the way.
Pi. Yes. I mean, you can, you just have to do it after I epsilon, putting to 0. Yeah. So this is the thing. So you see, whenever I'm calculating correlator with delta HA with one operator on the left, one operator on the right wedge, there are no epsilon 1-2s. So OL will still commute with delta HA. And similarly, when you calculate the commutator, usually what happens, you change the signs of epsilon and that gives the non-zero commutator. But because the epsilon 1-2 is not there, the commutator between OL and delta H will be 0. And similarly for delta H a bar, there is no epsilon 2. There is no epsilon, what is not there? There is no epsilon 2-3. See? There is no epsilon 2-3. And that is why delta H a bar and OR will commute as it should. But this only comes because of those I delta prescriptions that you have to properly resolve. And if you could have neglected all of these I epsilon factors, meaning for generic configurations where things are non-singular, so if you could have forgotten about the UV divergences, that is coming from this correlator and all that, then you will find that this 3-point function is actually the 3-point function with delta H form. So essentially the fact that, and you see delta H commutator, the result will be bad. Because delta H will be an operator, we will be in the operator in the future wedge. So it will not be an operator on the right wedge. So in fact, this ambiguities that you have between epsilon 2-3 and epsilon 1-2 in this delta H and delta H a bar, their difference will be not just a commutator, but rather commutator plus something which we call this contacts. It's not very easy to subtract them out because in one case, epsilon 1-2 is not there, another case, epsilon 3 is. Okay. So this probably will, present everything in a slightly different point of view, and it will be even nicer, even clearer. So now recall that delta H was this minus this. This was our expression that we got from Sarkar. So let me call the first term where the poles rotate clockwise as delta HA1, and the second term where the poles rotate counterclockwise as delta HA2. Now we said this before, if you just fix R equal to pi, then these operators are operators on the past wedge. And that's why we did not do that. Now let's regulate again R equal to pi minus delta. Remember that delta is greater than epsilon, greater than epsilon. Then these operators, this O2 that appears in delta HA1 and delta HA2, they take this form. Okay? So there is some factors of I delta that you have here. Now this actually will motivate us to define something that we call pseudo-local operators. So this is what I will call a pseudo-local operator, where O2 AB is xi2 plus added with some AI delta and xi2 minus argument added with some BI delta, where A and B can be plus minus 1 or 0. Now, consider this sort of operator where the arguments get some factors of I delta, fixed factors of I delta, like you have here. So for example, in this notation, this operator will be O2 minus 1, 0. Okay? Or O2 minus 0. So now if you take these pseudo-local operators and calculate correlator with another spectator operator, then you see this will be the correlator. So there will be some factors of AI delta, BI delta, but there will also be factors of epsilon 1, 2 coming from white. But because delta is bigger than epsilon, you can, in this term, for example, if you take O minus 1, 0, then in this term B is 0. So, okay, fine, delta term drops out and epsilon survives. But because there is a O minus 1, so here delta is there and it trumps epsilon 1. So in this term, in the xi1 plus xi2 plus term, there is an I delta but no I epsilon. So what it means? It means that if you take one of these pseudo-local operators and you study the divergence at xi1 minus equal to xi2 minus, that is resolved by standard Whiteman prescription.
That means on the right way.
Yes. So this is.
Yeah.
So over the dashed line, they will commute. Over the solid null line, this line, they will not commute because of this epsilon 1, 2. But over this line, this dashed line, they will commute because there is no I epsilon and I delta has some fixed signature. So even if you exchange them, this does not give any different sign of I delta. So this is why these are pseudo-local, that these sort of correlators, O minus 1, 0, the operators commute on the dashed null ray, but not on the solid null ray. And this is precisely the properties we actually need for delta HA. Because you see, this delta HA was operator like O minus 1, 0, but okay, if you also take into account 1 over W minus 1 over W xi2 plus and minus W xi2 minus, they are actually operator on the past wedge. This is as if, if delta were 0, this will be, as I said, operator on the past wedge. But now there is a minus I delta. So it will be a pseudo-local operator, but integrated over past wedge. Now, then they will commute over the dashed line. So this pseudo-local operator, which is integrated along the past wedge, it commutes with everything on the left wedge. And
exactly the answer to Abhijit's question.
Exactly the answer to Abhijit, hopefully. Yeah, so what I was saying is that, these sort of operators, O minus 0, they have this singularity structure. So you have, xi2, xi plus, xi minus. And they commute with this O minus 0, if it is here, it commutes with all operators on the right wedge. Because it does not have any I delta in the xi1 plus minus xi2 plus term. But it does not commute with operators which are, parallel to this xi plus axis.
Physically, it seems to me that your correlator is almost exactly as if it was, on the other side, except that the singularity is smoothened out. Right? Isn't that what this delta do? Smoothened out in a way that's different from the I epsilon.
Right.
So, very short distance properties are different. If you go a little bit away, it behaves exactly. So it's just some fuzzy approximation that doesn't do short distance stuff exactly right. Exactly like you.
Yeah, the way you want.
Yeah, so that's very satisfying.
Yeah. Yeah. So, but what I was saying is to complete that. So you see, but here this HS came with O2 minus 0, which I was calling, OAB was this. So minus 1, 0 is essentially where you have minus I delta in the first argument, but not in the second. But that is actually, the argument is not xi2 plus xi2 minus. The argument is actually minus 1 over W xi2 plus and minus W xi2 minus. So if you would have forgotten about I deltas, this operator that you have for delta HA1 is an operator along this in this past wedge. And that was the problem. But because it is actually not really O2, but O2 minus 1, 0, it commutes with everything over this dashed line, which I was drawing before, but does not commute with anything on the solid line. So then it is indeed the way delta H should be. And that was also seen in the 3-point correlator where epsilon 1, 2 was absent. So it's just another way of seeing this. Okay, so therefore we should be working with operators like this, but we should also keep track of all the poles that arise in the correlators. I mean, so far this was all operator expression, really. So there are some. Let me maybe skip that. You can get some operator expression for delta H by keeping track of all the mobile poles and fixed poles. Okay? And this will be an operator expression for delta H, which will yield precisely the previously studied 2 and 3-point functions that we showed with the resolved singularities. There are two special cases when this delta H acts on vacuum, which we saw in the 2-point function. In the pseudo-local operator language, it will be that some of the pseudo-local operators will be treated on the same footing as long as delta H is acting on the vacuum. So for example, let's say delta H is on the far right. That means epsilon I2 is positive for all I. And then for some of the pseudo-local operators, the distinction between I epsilon and I deltas are no longer there. So that will, intuitively that will make some of the operators on the same footing. And then you can check that this delta H will become, in fact, the delta H commutator from this expression. So there's some derivation of that. And the special case 2 is that if the spectator's operators are on the same, so if O1 and O3 both, let's say on the right, are both on the left, then you see that those ambiguous singularities are not present. Those ambiguous singularities meaning, which we had before, that O2 was here, and then O1 and O3, they were such that they were precisely hitting this hyperbole. But now if O1, O3 are all on the same wedge, then this sort of things will never happen. Okay. So then again, you will have delta H as a commutator contribution. Delta H should be a commutator contribution. And we will use them later, these two special cases. Actually, they will be important for satisfying the KMS condition. So let me go to that. Sorry, I'm getting late. So what are KMS conditions? 5. So KMS conditions. So KMS conditions are actually these 3 conditions, which I learned from some of these references. So one is modular symmetry. So a state vector must remain invariant under modular flow. So modular automorphism, the algebra won't change under the modular flow. And analyticity condition, which I thought was the KMS condition. But the point is that if all 3 are satisfied, then a modular Hamiltonian satisfying all these 3 conditions is unique. So if you run this backwards, if you have found something which satisfies all these 3 conditions, then actually the modular Hamiltonian that we have computed for excited states is properly computed. So you might say, okay, what about 4-point function, 5-point functions? You have not considered that. But the thing is that the delta H we have calculated up to 3-point function already satisfies these 3. So we know that our results are done. So first check the modular symmetry. H acting on a state must keep the state invariant. So H acting on a state actually gives you this, but this should be equal to 0, because remember modular symmetry was this condition, so H acting on omega must be 0. But because the modular symmetry condition is where H acts on vacuum, effectively delta H is a commutator contribution, which was special case 1. And then these 2 terms cancel out and you indeed satisfy modular symmetry. Okay, so endpoint there is also one point is that when we did have the endpoint contribution, we can show that it also precisely annihilates the vacuum. So this is something Omkar also said in operators annihilate. Analyticity condition that we had here, So you can expand that, and it becomes some statement about 3-point functions, but luckily we have computed the 3-point functions. However, this analyticity condition says that for any pair of operators A and B in the algebra A, so they are always on the same wedge. So we have to compute these 3-point functions where A, B are both on the same wedge. But even then, we have seen this special case too, that delta H is the commutator. And then you can explicitly check that the two sides, it's a nasty expression, but these two sides actually match up. The modular automorphism is the most interesting one, and we are treating that or investigating that using this double commutator test. So this double commutator test is you have two nested commutator where you first take delta H with OR and then take it with OL. So it has to be 0. And then again, let's go back to the expressions we had precisely for OL, delta H and OR for any operator ordering. And this absence of the epsilon 1, 2 and epsilon 1, 3 in the first term, and similarly for the second term, it will tell you that, for example, ordering between OL and delta H and OR, they are irrelevant. This is what I already mentioned. And indeed, I mean, these epsilons were actually had their origins in I delta. So actually that I delta prescription was responsible. So this is the summary, last slide. So commutator contribution is saw gets modified either through endpoint contributions, I did not discuss too much about them, or via some contact terms, which I have not explicitly showed because of time, but you can calculate them. There are subtleties with complex modular flow, which we discussed, and there are ambiguities, which if you resolve properly, that ensures that it satisfies KMS condition. Because you see, if delta H were just delta H commutator, then these double commutator tests will never be satisfied. Because of this absence of few epsilons is why it is getting satisfied. There are a few open questions. Thanks.
Second order change has not been completed.
No, only for stress tensor perturbation, which is easy.
There is some universal result. Second order change in entanglement has some proportional to central charges. Second order change in entanglement.
For general examples.
For share you want for A not share.
Yeah.
Sure.
For delta 2H.
Yeah, and delta to S.
S.
It has a proportional to the central. Can one show that from this?
Yeah. I should add that to the list of questions. Okay.
Do you have in mind like a holographic interpretation?
Yes.
Something like
Yes.
that. Imagine finding.
Yeah, I mean, we were originally motivated because of this intersecting modular Hamiltonian way of computing, doing bulk reconstruction. Then for excited states, how to do it. So you need to know these excited state modular Hamiltonians.
A very stupid question. So this delta HA that you're computing the correlator with, should it not be like, on the A side, you are working with the modified state, while on the A bar side, you are working with the unmodified state. So there should be some bad properties, sense that you should see, as long as we're on this side are causally connected to the A side, you should see everything like that state where your operator inserted, and as you go on this side, you should see as if you are working in the right state. Maybe this is very stupid. I mean, then the picture is of course very, very bad looking picture. What is wrong? I mean, there is zero thought expectation of this sort.
So you have delta HA, and what are you computing?
So you're computing correlations functions of some probe operators with delta HA, right?
Okay.
Delta HA
In which state? Vacuum state.
vacuum state,
Okay.
right? So then I was thinking that delta HA is like modifying the state from vacuum state to this other state, deformed state, but only on the A side,
Mhm.
right? So as long as you are able to see that, you will see as if you are in this modified state,
Mm.
right? But if you go on this side, on the left side, where you are not related to this concept, then you should see this they are working in the vacuum state. Some picture of this sort should emerge, right? I mean, it's a very bad picture because there will be sudden transition as you cross this light cone and so on. But then I just want to understand that this is probably not what one expects. What exactly is not here?
Off the top of my head, what comes to mind is these 3-point functions that you have studied. They come with some asymmetric I epsilons. So maybe that's what will ensure that.
No, but Abhijit is saying it's not just singular. Nothing should change on the left.
Nothing should change, meaning
Meaning is
What-
that you put your operator insertion on the left, and it should be the same as just doing everything in vacuum.
On the right side. Yeah, but that's like you're modifying the state only on this side, right?
No, it's not unitary. It's a function.
probably that can be changed.
If you have a local operator that's just on the right, that does not mean that.
I see. So it's not like now that I trace out this other guy and I see the same density matrix on the left. Because I have inserted this operator on the right side.
Yeah.
I trace it out. It will be
Yeah.
part of
It will be.
it will change the density matrix. So
But suppose you insert this. Suppose you inserted it with an into the pi.
then it's
First order in H, is there a difference?
I see. Yeah.
Yeah, you get your counting.
Sorry.
You that's not e to the I. is.
What
That's
is the difference at first order?
no, it cancels out because you get a counting. Not.
Oh.
Yeah.
I see. Okay. Thank you.
Anything for the balance? I think that's fine.
Yeah.